Okay.
So, extremal principle is a problem-solving strategy which considers extreme objects that maximize or minimize a thing. So we'll see examples of this soon. And why extreme objects are useful? It's because there's nothing more extreme than them. You get it? So we'll we'll see some examples soon. So our first example is uh, let S be a finite set of distinct positive reals. For every pair of elements A, comma B in S, the element root over A squared plus B squared is also contained in S. Prove that S contains at most two elements. So this is a very easy problem. So so let's say X is the max. So let's say the set is finite for the sake of contradiction.
Can you show the problem again, please?
Okay. S is a finite set of distinct positive reals. So that for every pair of elements A, comma B in S, root over A squared plus B squared is also contained in S. Prove that S contains at most two elements. Have you gotten it?
Yes.
Okay. So let's say X is a finite set with three or more elements that satisfies this property. And let's say it's also finite. Then I will show that. Then the thing is, we must show it has at most two elements. So let's say it has three or more elements. So I'll just give an example of a set that can satisfy this. Let's say the set originally contains 4, 0, and 2. Then it also contains root over of 20. Is that fine? And then you can keep on get root over 24, root over 28, etc. And if you notice, for it to satisfy this property, if it doesn't contain two elements, then you soon might start to notice that this set will turn out to be infinite. So how do you formalize this? This is where the extremal principle is very useful. So let's say it has three or more elements and it's finite. So then you consider the maximal element. Let's say it's A. And now, because it has three or more elements, you know another element is non-zero. Let's say that's B. So we also know that root over A squared plus B squared is in the set. And since this is a positive number, as this is a set of positive reals, we know that this must be greater than A. But that's a contradiction. You know why? Because we assumed A to be maximal. Is that okay with everyone?
Yes.
Anyone has any doubts?
No.
Wait, could you repeat?
Oh, who is this?
Sharanya, me.
Okay. So what did you not get in my explanation?
Like, could you repeat it once again? I didn't catch.
So our approach is sort of like trying to prove the contrapositive. So if it satisfies this property and it contains two or more elements from here, then it's not finite. That's our approach. Is that fine?
Yeah.
So let's say it's finite and it has two or more elements. No, it satisfies the property and it has two or more elements. So let's say one element is 7. And since it has three or more elements, one of those elements is non-zero. Let's say 4. Okay. So we get
Okay.
7 squared plus 4 squared is in the set. And then we can apply it again on this. We get root over 7 squared plus 2 into 4 squared is in the set. On and on and on. But so it seems like the set is infinite. But the way to formalize this is by considering the maximal element. So let the maximal element be A. We know there's another non-zero element which is B. So we should have root over A squared plus B squared belongs to S. But root over A squared plus B squared is greater than A. But we assume A is the maximal element in S. That's a contradiction.
Okay.
So there can't be
Got
a
it.
maximal element in S, and hence S is infinite. So I'll just sketch it. The positive maximal element. Now the next example will outline. I will also use it to outline some common mistakes while using the extremal principle, because many people forget to do this sometimes while doing an extremal argument, and I have fake solved many problems due to this loophole. So, this problem states you have an infinite chessboard. Each square has been filled with a positive integer. You must show that each each integer in a cell is the arithmetic mean of the four neighbors. You must show that all integers are equal to each other. So anyone has any ideas how to do this?
We just contradict the maximality. So if there exists a maximum element A, the arithmetic mean of its neighbors should be equal to A. So at least one of them should be greater than A if there exists one which is less than A.
Okay, so if I'm getting you right, you consider the maximal element, and then all of its neighbors must be equal to it, right? That's what you're saying.
Yes.
Okay, that's a very good idea. But there's one small loophole. You're given positive integers. So there may not be a maximum. There may be like a subset of positive integers most likely doesn't have a maximum. Like you can consider something like this. There will be no maximum. It'll go on to infinite. So we do what you did, but with a slight modification. What?
Take the minimum element.
Yes, perfect. Okay, so as a quick write-up, let's say the minimum element is here, and its four neighbors are A, B, C, D. We know that A plus B plus C plus D is equal to 4m because of this condition. But because of the minimality of m, we get that A is greater than or equal to m, B is greater than or equal to m. So for the equality case to hold, all of A, B, C, D are equal to m. And then we keep on doing this again and again till the entire grid is filled. Okay, guys, if this is going a bit slow for you, please DM me. I'll send you a nice buffer problem. Do you guys want me to go faster or slower? Don't be scared to say faster. I'm not evil.
No, this pace is okay, thanks.
Okay, some people are saying faster. Okay, so I'll go a tiny bit faster, not way too much. Okay, so now, okay, some people are asking for the buffer. So these are the 6 buffer problems. Just take a screenshot. And the ones I've highlighted blue are the ones which I like a lot. You can also do the other 2 if you want. Okay, so I'm assuming you guys have taken a screenshot. Okay, the next problem. Oh, I forgot to mention. In this, someone brought up a very good thing about when the maximum and minimum exists. Now, if you have an infinite set of real numbers, you cannot say that the minimum exists. Because you can just take this set of reals. It has no minimum. You can't even say 0 is the minimum. So sometimes you have to be very careful about when you're applying these arguments. If you have a set of negative integers, you cannot apply a minimal or maximal argument. You could apply maximal, but not a minimal. If you have a set of integers, any integer, not positive and negative, you can't take the minimum or maximum. Got it? Okay, someone has a question on axiom of choice, but I don't get what they mean. Could they unmute and speak? Hello? Mandar? Okay, whatever, let's forget about that. Okay. Wait, were you about to say something? Okay. So now it comes to the next problem, which is a more interesting problem, unlike the previous two. The previous two just outlined the power. Now this is an actually interesting problem. So let's say you have finitely many red and blue points on the plane with the very interesting property that every line segment is a key word, that joins 2 points of the same color contains a point of another color. Prove that all the points lie on a straight line. So I'm going to give you guys 2 minutes to think about it. If you have any solutions, you can speak out. Anyone has any ideas? Even if it's a bit dumb, feel free to speak up, even if you think it's not right.
Okay, I guess we can assume that 3 points are not on a straight line. If they aren't, if all the points don't lie on a straight line, there must be 3 points which are non-collinear. So if they're all the same, we get some infinite descent of triangles.
Yes, that's a perfect intuition. And the point of extremal principle is that you can formalize that intuition. So the best way to formalize it with extremal principle is to consider the triangles with minimal area. Is that all right with everybody? So if you don't get what I mean, I'll show you. So let's say there are finitely many points and they don't all lie on the same line. And since there are finitely many points, there exists a triangle with minimal area. If they're infinite, then you can't say that. But since they're finite, you can say that. That's a key detail. Let's say these are the 2 red and 1 blue. Now, by our interesting property, the line segment joining the 2 red has a blue point on it. But now you can repeat the same thing. So you get that this line segment has a red point on it. And then you can repeat it, wait, wrong color, again and again. That's the intuition Bear was talking about. And the way to formalize this is by considering the minimal area. Because let's say you take the triangle with the minimal area. In this triangle, let's say without loss of guarantee, these 2 adjacent vertices are blue. And this one is red. Then you get another red point here. And on this, you get a blue point. But that's a contradiction, isn't it? Because you assume its minimality. So then we
Yeah.
get smaller. Okay. So are you guys all fine with it? Also, can you guys please switch on your cameras? It feels like I'm talking to a bunch of people who don't exist. Hello, anyone? Thank you, Mandar. Anyone else? Thank you. Oh, hello.
Hello, I'm in a
Really
car.
good.
But
Okay, so that's good. A bit better. So, am I going a bit too slow? Should I speed up? Should I slow down? Hello, guys. Okay, some people are saying to speed up.
Thoda speed up works.
Okay. So, have any of you seen this problem before? Okay, if you read Rashilba's book, you
Yep.
would have.
Seen it.
Okay, then you can work on the buffer problem. So this is a nice problem. I'll give you guys 4-5 minutes to think about it
Wait,
since it's
could
harder.
you show the buffer again?
The buffer, yeah. Wait, it's a bit blurry. Wait, can you guys read it clearly since
Yeah, got it.
okay. Oh, someone's asking to zoom. Wait, maybe I'll remove the highlight. It might be.
Okay, so like I've sent the problem on Discord general, so people can check.
Okay. Okay, think about this problem for 5 minutes and then I'll discuss it. Tell me any ideas you get in the next. Also, can you understand my handwriting? Everyone? Okay, good. I'm taking that as a yes. Okay, anyone has any ideas in this? Hello? I'm sure you guys can't just be staring at the screen doing nothing. Any ideas?
So if we consider like two segments, if we just do a first, we just draw them randomly. And if we consider two segments, so two blue points and two red points which are connected, if they intersect, we swap how they're connected.
Okay. Okay, so your idea is, let's say we have these 5 points and these, wait, 1, 2, 3, 4, 5. Oh, that's 7, sorry. 7 red points. Instead of trying to find the matching, let's just randomly make a matching, and then if there are any errors, we'll fix it because we're too lazy to find the proper matching. Let's say this is it. Okay, so this is a intersecting, so you can swap it. These. Yeah, so that's it. We got a matching to our process. But now the thing is, what if we keep on doing this again and again? That's a problem. Let's try finding an invariant. No, not an invariant, a monovariant. Let's just try it. We get this. Someone's unmuted. Also, guys, please mute your mic. Oh, so let's try finding a monovariant. So a dumb guess could be the number of intersections. But that may not work out, right? Like, I'll show you a good counter example. We won't have to open the doorbell. 1 minute. Okay, guys, I'm back. So that may not work for the following reason. Let's say there is a blue pen. Let's see, this is our system. Let's just add one more. And we do a process. Now, our guess monovariant was the number of intersections. But if we undo this, and then we draw the Newton, the number of intersections actually increased by 2. So that's not a suitable invariant. So, yeah, better.
But if after this, we look at all of these ones that we have had, connect this blue to that red, connect the blue to the first red on this link which meets, then it connects like that blue to the next red, that blue to the next red.
Yes, that's a good idea. But the thing is, this might not be the only such structure when new points are added, new intersections are added.
Yes, but we can try recursively,
Hmm.
and then eventually it should stop.
Those are good ideas. But someone on DM me send me a better idea. What if you consider this sum of the lengths? So at a local level, you have, let's say, a red, a blue, red. Okay, now this is an exercise left to the viewer. You can repeatedly apply triangle inequality and get that AD plus BC is less than AC plus BD. So you can keep on applying this until you stop, because eventually you'll have to stop, since there are only finitely many possible values the sum of the lengths of the segments can take. And eventually you stop. And when you can't apply the process anymore, that means no segments intersect, right? And this is where another example of extremal principle comes useful. Sometimes extremal principle is not useful, does not directly kill the problem, but it's useful to write up the solution with extremal principle. Like, you won't think of the extremal idea first, So after you solve the problem, you realize, oh, the extremal principle can be used to write up the solution cleanly. So in this case, the way you can write it up is, out of all of the finite many matchings, you consider the ones whose the sum of the lengths of the segments is the minimum. And then due to this argument over here, oopsies, you know that in this segment there can be no crossings, because if there was a crossing, you have a matching which has a total sum which is less, which is a contradiction, right? Because we assume minimality. Okay, are you guys getting it? Any doubts?
Yeah, it's good.
Going too fast? Or have I been too slow?
think
Not
it was IMO like question.
What are you saying? I can't hear you.
I think this problem was in IMO shortlist 2013 or like that.
I don't think so, because I think it was a Putnam 1979 problem. Yeah, it was Putnam 1979. Okay, can more people switch their cameras on and tell me if they understood? Because I've only gotten 4 or 5 people who said they've understood out of 22.
yes.
Okay, good.
I have understood.
Okay. Oh, I was talking on mute. Okay, so let's move on to some of the more advanced problems. So, which one do you guys want to do first? Oh, actually,
First one.
actually, Manda's name is named after the second one, Sylvester Gallai. The second one is Sylvester Gallai theorem. Okay, since someone was saying first one, let's do the first problem. Oh, now I can switch my camera on. Wait. Hi, guys. This is me. Most of you have already, whoever has the cameras on have already seen me. Okay, so we're doing the, okay, Beirut.
Yeah, so we just take the most extreme to the right of the points then, right?
Yes, that was my first idea. Like you take the most rightmost point, and then from the rightmost point, you take the topmost point. Okay, so
Yes, it is a finite set.
I'll explain my solution. So we assume, wait, let me just copy paste this. Okay, so we have to prove this set is infinite. So let's try proving that if this set is finite, then there is some point which does not satisfy the property. Okay, now convince yourself of the following fact. Like, it's not obvious, but if you have a finite set of points, you can in some sense choose the rightmost point. So in this case, this is the rightmost point. And the rightmost point can be formally defined as the point with the maximal x coordinate. And from all of the points in the x maximal x coordinate, you can take the one with the maximal y coordinate. Now can anyone answer why this point cannot satisfy the following conditions, the given conditions?
Because it has to be a
Because-
midpoint of another vector segment, so it can't be midpoint.
Yes, because if, let's say the midpoint is 2 points. Now, if one of the points is to the right of this point, then we will get a contradiction because we've assumed it to be the rightmost point. So it has to be the midpoint is something on this horizontal line above and below. But why is that a contradiction? Anyone?
The uppermost point.
Yes. That's the solution that I thought of. Now there's another solution which also uses extremal principle, which in the handout I saw this in, that was the solution originally given. So I'm gonna give you guys 2-3 minutes to think of that solution. Well, let me just write this down. Okay. So considering the convex hull, someone said, could you just elaborate more? Yeah, considering the convex hull is a good idea. Yeah, that does work, because if you consider a point on the convex hull, you will get that point, the 2 points which has the midpoint as that, they must both lie on the convex hull. But if you take a vertex of the convex hull, there'll be a contradiction. That's also a very nice idea. This is sort
Yeah.
of what we're doing here.
That's actually same as what you do.
Yeah,
Just
sort of what,
put their coordinates differently.
yeah. Okay, so do you guys want me to give the other extremal principle solution?
Give hint first.
Okay. I don't know how to give a hint without ruining it. Okay, Beirov?
Right, sorry, this won't work. I was thinking, what is the maximal length between two of the points?
That's
But
exactly the right thing.
what?
Yes.
I thought it wouldn't work.
Okay. So let's say you have the maximal length AB, which is the maximal length, and you're assuming this is finite. So the maximal thing has to exist. So let's say B is the midpoint of two points C and D. Now we'll do casework based on whether AB is perpendicular to CD or not. If it's not perpendicular, you know at least one of these angles must be obtuse. Since they sum up to 180 by, so without loss of generality, we'll assume that angle ABC is greater than 90. Now consider the triangle ABC. Because angle ABC is greater than 90, we know that angle ABC would be greater than angle BCA, right? But due to a very trivial property of geometry, we get that AC would be greater than AB, because the angle opposite to the side opposite to those angles, right? Everyone follows? Okay.
Yeah, that
So that gives us a contradiction, right? Now, if AB is perpendicular to CD, we also get a contradiction, right? Like this length has to be greater than AB to the Pythagoras theorem. Wait, you could have applied what we did over there also. I overcomplicated it. But yeah, you guys get the point, right? Hello?
Yeah.
Yes.
Okay. Okay, we have way more time than I expected. I thought that this would take most of the lecture. So let's discuss the theorem which Manda named himself after, Sylvester Gallite theorem. So let me just highlight it. I think easy to highlight. But yeah, this is the theorem. Please. So it basically states that if you have a finite set of points on the plane, not all of which are collinear, then there exists a line which passes through exactly two of the points. So if every line passing through 2 points passes to a third point basically, then all points lie on a straight line. That's basically what it's saying. Okay, so I'm going to mute. Tell me if you have any ideas.
Maybe you could have a proof by induction. So if there are 3 points, not all of them collinear, we can prove there are 4 points. And with that, we can prove there are 5 points. And so on.
Okay, that might work. Okay, Avni, what's your proof?
Oh, sorry. You can just assume that all of the lines contain uh, all lines contain three or more points, but like not all of them. And then uh,
Okay. Oh, also, Bhairav, there is a slight mistake in your proof. I'll message you later with the proof, with the mistake. Just think about it for a short while, but it's wrong. Okay, so I'll give a nice extremal proof. Now, I don't know how to motivate this, And I guess it's not meant to be motivated. It took about 15-20 years until this was solved with an extremal thing. The extremal thing is quite elementary, but this was originally posed as a problem, I think, by a mathematician named Sylvester. He noticed it while studying algebraic curves, and then he conjectured that this was true, and he sent it to some of his other friends, and this guy thought of a very non-trivial solution, non-elementary. And then later, I think a guy called Galley found the extremal principal solution after about 20 years. So, um, yeah, Omit is nice. So, wait, do you guys want to work on it a bit more, or should I give the solution? Hello? Okay. Yeah, I'm gonna show why induction fails and some other approaches fail. So, Bhairav, this might answer your thing. So, okay, so first I'm gonna show why induction fails. So, I'm assuming Bhairav you meant inducting on the number of points n. So the thing is, the reason it fails is while going from n plus 1 down to n, you can't just delete a point. Because you know that your assumption is that the line through any two of them passes through the third, so you want to show all of them lie on a straight line. But what if the line going through two of them passes through the third point? Then you can't use the induction hypothesis.
I didn't mean like that, as in, I meant if it has 3 points, non-collinear, then it must have 4 points, not all collinear, which means it must have 5 points, not all collinear.
Why must it have 4 points, not also linear?
Because if there are 3 points, not all collinear, then a line passing through two of them will not have a return point on it. So there must be a fourth point, and a fifth point, and a sixth point, and so on.
But then why fail at some point? Because then you might get 2 points, 3 of those points after a certain amount of steps that are collinear, and then you may not be able to apply the step anymore.
Yeah, yeah, that's the issue.
Okay, so I'll show some other extreme arguments which me and a friend of mine thought of while solving this. So my friend's thing was this is actually quite motivated. So you want to show all of them lie in the straight line. So a good idea could be if they're not on the straight line, you could consider the minimal angle. Now you want to show that it's somehow zero. So if you have the minimal angle, you want to find something with a smaller angle and then another smaller one, which would be a contradiction. So let's say you have these 3 points. And this is the one which minimizes the angle. And you know that there must be another point on this, right? So out of the new configuration of angles, a good idea could be, let's say, oh, it could also lie over here, which will be a separate case. Let's say finding something which has a smaller angle value. That's a very nice idea. But the thing is, it doesn't work. Because you can explicitly construct cases where it doesn't work. So another example thing could be, so you have a line which passes through most of the points, and you have another point which is not on this line. Now you feel a bit frustrated, right? because that's the main structure you have, and you want to somehow show that the point lies on the line. So what do you want to basically want to show? What is something you want to show? Something that you can try minimizing, and you can show that you can find something with a smaller value than that. Yeah, Bhairav?
The distance from the point from the line.
Perfect. So you have, let's say a different color. This is the point, and you drop the perpendicular. Now, since we have 3 points on this line, what we're trying to minimize is from all finite pairs of points and lines P and L, and L is the line passing through 2 of the points. You want to minimize the distance from P to L. So since we have 3 points on this line by our assumption, since we're taking contrapositive, 2 of them will lie on one side of the perpendicular, right? Now anyone knows how to finish off from here. Okay, so should I spoil it, or do you guys want to work on it? So I'm taking that as you guys want to work on it more. Okay, so some people are saying that they want to work more on it, so I'll give them that time. Okay, few people have wanted a hint. So the hint is, like all extremal principal problems till now, we assume something is minimal and we want to find something which is smaller than that. So we want to get a contradiction. So where do you think that we can do this here? Any ideas on how to do that? Wait, did you guys understand the quantity I was talking about here? Which I gave the hint on trying to minimize that Beta also talked about. So do you guys still want more time or should I give the solution? Okay, so I'm taking that as a no. So I will, if you guys want the solution, you can DM me on Discord after the class. But you can also work on this later. So you could just take a screenshot of the problem if you're interested in doing it later. But I've given you guys already a big hint on what to minimize. Okay, so I'm assuming you're done taking a screenshot. Let's move on to which problem do you guys want to do? Since all of these are really nice problems. Oh, also this sixth problem is very similar to Sylvester Galley, which is the problem we were just discussing. Uh, it's very similar. In fact, some of you may think of it as the projective dual of Sylvester Galley. Almost identical. Okay, so some people want the convex polyhedron problem. Is everyone fine with that?
Yeah.
Okay, perfect. So we're given, so we have to prove that any convex polyhedron has two faces with the same number of sides. So try it out for a while, and then if you have any ideas, feel free to speak up or DM me.
I have some ideas. Can I say?
Oh, you could DM me, that would be better. Don't spoil.
Okay. Okay, fine.
Oh, for those of you who don't know what a polyhedron is, it's sort of like a 3D polygon. Uh, it's like a cube could be a polyhedron, a pyramid could be a polyhedron, and it doesn't necessarily have to be regular. Like there can be some faces with three sides. There can be some faces with 10 sides. Like they can have both. Okay, anyone has any ideas? Okay, so should I go over the solution? Hello?
Yeah,
Okay.
I
So,
don't have any ideas.
okay. So we want to prove that two have the same number of sides. So a natural idea could be pigeonhole principle. So you have a bunch of pigeonholes and you want to fit the faces in it. So you want to show that there are more faces than there are pigeonholes. That's a very natural idea that could come to someone's mind. But the thing is, how do you bound the number of pigeonholes? So let's say it's a cube. Each has each face has four sides, right? So there should be four pigeonholes from 1 to 4. So in general, if the maximum number of sides is n sides, we want to have n pigeonholes from 1 to n, right? But then there's another neat observation about polyhedrons. A polyhedron, each side has to have each face has to have at least 3 sides, right? I can't have 2 because each face is a polygon, and a polygon needs 2 sides or more.
Yes.
So you have pigeonholes. Oopsies, wrong pen. From 3, 4 till n. Now these are n minus 2 pigeonholes. And if we show that the maximum number of sides a polyhedron has is n, we want to fit at least n minus 2 pigeons, which is the faces, into these pigeonholes. Does anyone know how to finish from here? Because if the side with the maximal thing has n sides, each side is connected to a face, right? So it has at least n faces from the neighboring and one face over there, right? So there are at least n plus 1 sides, and we have n minus 2 pigeonholes. So by pigeonhole principle, 2 of them have the same number of sides. That's basically the motivation. But that's a bit of an unneat solution because we can cut out many redundancies. So in short, we consider the face with the maximal number of sides. Let's say this is 7. Now out of its 7 neighbors, the number of sides each of those 7 neighbors can have ranges from 3 to 7, which there are 5 possibilities. So by pigeonhole principle, 7 of those neighbors, they can only have 5 possible number of sides, right? So 2 must have the same number of sides. Everyone getting this?
Yes.
Hello? Okay, good.
So where is the
Yes.
extremal principle involved here?
Yeah, because I mentioned the maximal number of sides, which faces the maximal number of sides. Because that idea it wasn't some random idea. It came from the fact that you want to do pigeonhole principle. And if you want to bound the number of pigeonholes, you want the maximal number of sides that there is in a polygon. Is that all right?
Okay.
Nice. Oh, and most of the problems that I'm doing are usually killed by extremal principle. Like extremal principle can make the problem trivial, but that's not always the case in Olympiad problems. It many times is, but many times extremal principle is just a step, and extremal methods of thinking can be very useful. So a good example of this is IMO shortlist 2022 second number theory problem. So that's a very nice problem which extremal principle doesn't make it trivial, but it's a nice thing to think in an extremal lens. Oh, that reminds me, there are some other applications of the extremal principle to number theory. So it's similar to infinite descent. Yeah, so it can be used in number theory. So I'll give a quick example. Wait, let me just find a good example. Yeah, so let's say you want to prove the equation x squared plus y squared is equal to 3u squared plus d squared has no solutions in the positive integers. Okay. So now, this problem, if someone sees it, the first idea will not be extremal principle, and most likely it shouldn't be. But after you solve the problem, it can easily be phrased in terms of extremal principle. So let's say you have a solution to x squared plus y squared is equal to u squared plus t squared. Now, for those of you who know modular arithmetic, we get that x squared plus y squared is equal to 0 mod 3. Wait, do all of you know modular arithmetic, or should I just...
We
Yeah, we
know.
know.
Like, yeah.
Okay, we get that x squared plus y squared is equal to 0 mod 3. And now, why does that imply that... Now, can we infer that 3 divides x and 3 divides y?
Yes,
Okay, why?
because the square is either 0 or 1 mod 3, and if
Yeah.
at least if one was one of at least one of them was 1 mod 3, then it would be 1 or 2, which is a contradiction.
Yeah, that's right. So if at least one of then this sum would be equal to 2 to 1 or 2 modulo 3. So because of this, we get that 3 divides x and 3 divides y. Now here is where the main step comes. Because 3 divides x and 3, wait, let me just move this all up. Because 3 divides x and 3 divides y, we get that x is equal to 3a for some integer a, and y is equal to 3b for some integer b. And if we plug it back into a super nice equation, we get that a squared plus b squared, 3 times a squared plus b squared is equal to, which variables did I use? U squared plus t squared. Okay?
Shouldn't there be 9? Like 9 square
Yeah.
plus 3 square?
So I skipped few steps. So you get a 9a squared plus 9b squared is equal to 3 times u squared plus t squared. And then I cancel the factor of 3 out.
Oh, yes.
Okay, is this all fine? But now we have another, oopsies, wrong. We have another set of variables a, b, u, t, which satisfies the equation. So what can we do on this? Yeah, Bedrav?
The extremal principle or infinite descent or induction.
Yeah. So we can repeat this procedure again, what we just did. To get a new solution, let's say x1, y1, z1, t1. And then again, and then again. And we'll keep on getting smaller solutions. But that's a contradiction, right? Like you can't just keep on going down and down and down in the positive integers. So a nice way to phrase this would be, let x out of all the solutions, since all the solutions take up positive integers, from all the solutions, we take the solution which minimizes the sum, x plus y plus z plus t. We take the one which minimizes the sum. But through our procedure, we get that x by, we get that z comma t comma x by 3 comma y by 3 also is a solution, right? But we know that the sum of these elements is less than the sum of these elements. But due to our assumption of minimality, that's a contradiction. So yeah, that's a nice way to put it. And like the previous problem in the crossings, the extremal principle isn't the first idea you'll get, but once you get the solution, it's very natural to frame it in terms of extremal principle. Okay, so we have just 10 minutes left. So wait, where are the buffer problems? Yeah, so which problem do you guys want to work on? Oh, after class, you should try this problem. All cross sections of a solid are circles. Prove the solid is a sphere. And I have a very nice story with this problem. So I saw this problem in a book and I tried working on it for 45 minutes. I got nothing. So my instinct was, why not bash it? So you get that the equation of 1 Yeah, so where was I? So you can, so my thing was to bash it. So you get that the equation of the solid is f of x comma y comma z is equal to 1. And then you algebraically represent that each cross section is a circle. I even asked Pranav for help on that, but that didn't work out. So Pranav is the bash master for those of you who don't know. Okay, so which problem do you guys want to work on? I think we're running out of time. So I don't think we have time to discuss any of these problems. So Sanjana Didi, can we end this class a bit early?
Okay, sure. Or should I stop recording? If you want to end now.
Yeah. Good.